So my name is Fedor. Have my first time at this conference, and I ended up presenting twice. This is the first one. So we're going to talk about undefined behavior. Who here has been at CppCon and saw Ansel and Barbara's talks, one of two talks on undefined behavior? Okay, so that's not that talk. I do performance-centric viewpoint, although I will also be giving you kind of my personal take on some of the ideology behind undefined behavior. Who have seen Chandler's talk on undefined behavior? So a lot of what I'm going to say was inspired by his view on it, and so I do refer to some of the things he has presented. All right, so let's talk about what's going to be shown and what's the motivation. So it's undefined behavior, not undesirable behavior. We'll talk about what it is, what it isn't, some language hair splitting, why is it there, and a lot of the why questions actually have to do with performance, so this will lead us into performance. And when we try to understand performance implications of UB, it will naturally lead us to the interaction between UB and compilers. And then we'll talk about basically, UB as a weapon, if you wish, how to defend against it and how to wield it. So the concept itself is defined in the standard, and that's the simplest way for me to introduce it. So if you know what it is, well, the standard has these exact words. The standard either says that the result is undefined, or it says that it's not a well-defined program. Now, in particular, so in this example, if there is a signed integer overflow, then according to the standard, the result is undefined. What does it mean? It means that the standard imposes no requirements on what the result will be. Now, one thing that is important to point out is this is not compile time specific. There are cases where UB is basically baked into the code at compile time. This is runtime. So the standard says if k is less than int max minus 10, then everything is fine, result is defined, the standard defines exactly what this function should do. This is often the case, but not always the case. Sometimes you get something where the standard just says, if you write this, it's undefined, period. Yeah.
I disagree with your second bullet point. The standard imposes no requirements and restrictions on the result of f. Actually, it's the behavior of the program that calls f.
Oh, we'll get to that. Okay, we'll get to that. Yeah, so you're right, but you're like jumping to a few slides forward. Yes, Tim?
I think the program as a form is also not, that's something else, that's like a compiler error.
I think you're actually right on that. I remember editing the slides on this, and program is informed. The diagnostic, they have to say diagnostic is required or diagnostic is not required. Yes, after that. Yeah, you're right. I remember editing the slides and I missed this one. Sorry about that. I edited the few later ones and somehow I missed this one. Okay, so now here is some UB lore for you. If your program exhibits undefined behavior, anything can happen. So all of those things are possible. Now, the intent behind this was in some way good. It basically tried to scare the programmers away from undefined behavior. The results, in my opinion, are not good because, well, A, in practice, none of those things do happen. And the programmers, the other thing is, well, yeah. The other thing is the programmers start to reason about undefined behavior. The programmers start to reason, and what the programmer says is, well, at the end of the day, the compiler has to generate some machine code. I mean, if it doesn't issue the diagnostic, it will generate the machine code. A machine code running on this machine is limited to whatever that processor and the hardware is capable of. Launching nuclear missiles isn't in the cards, not from this. And the problem with programmers reasoning about it is, they're right insofar as, it's not going to launch nuclear missiles from here. But then they take it like further and start saying, okay, what could the compiler reasonably emit, and what could the hardware reasonably do with this code? And that's where we get into trying to sort of define and practice undefined behavior, and that's where things start to get hairy. So on one hand, in my opinion, over-exaggeration of dangers of UB, undefined behavior, in practice leads to the programmers underestimating it. And just like I'm saying, it shouldn't be this, giant specter used to, terrify bad children at night. It also should not be underestimated, because in many ways, even though, if you look at the lore, it's actually not as bad as people say. In many ways, it's worse than people say. So the true danger, that's why I told you you're jumping the slide, is that not just the result of the calculation that has UB is undefined according to the standard. The standard imposes no requirements on the entire program that encounters undefined behavior anywhere. So in particular, as Marshall said, any program that calls that function with an integer overflow, with an input that causes integer overflow, the entire program is undefined. And we'll actually see live examples of that. Now, at the same time, it's important to remember, no, you don't get any special powers. You couldn't do anything you couldn't do before. So there is this balancing act of both not overestimating it and not underestimating it. So here is where programmers get into complacency. They say, well, I plus 10, it causes integer overflow. Okay, fine, I won't get the result I expect. But it has to be something, it's going to add two numbers. The hardware will do whatever that hardware does. So maybe it's different on different hardware, but it has to be something, and that's the limit. That's not true. That's not true. The true danger is that the entire program becomes undefined if any of its operations exhibits undefined behavior, and that goes both backward and forward in time. And I'll show you. I'll actually show you that. So it's important to remember that undefined behavior anywhere in the program taints the whole program, not just everything that comes after, but the whole program. Yes, Mark.
Oh yeah. I was also going to say, the other thing is if you don't call F, you don't invoke undefined behavior, and your program is reasonably well behaved.
Or if you don't call F with a K large enough, then you're fine. Mm-hmm. Yeah, that's absolutely true. Okay. So how could the UB taint the whole program? Well, okay, first of all, let's assume that the compiler can see the body of this function when it compiles the entire program, so everything is in line. The important part here, the fundamental kind of part to understand of how one little UB taints the whole program is, basically you could say the compiler is not required to condone your undefined behavior. Or it can make assumptions that undefined behavior does not happen. we'll work through that logic in a little more details. So now, what happens in practice? Well, you can actually run this, and in practice you're limited. I mean, something will happen. The program will compile, and it may produce an integer result, or something else may happen. But you can try, you can find out, and even if you can live with what happens, first of all, there are no guarantees that it will keep happening. Second, a different compiler might do something else. And third, even if in this particular situation you're actually okay, for some definition of okay, in a very similar situation you won't be. All right, so let's look at this code. Okay, I don't have any pointers here. Well, let's see. Okay, they asked not to use laser pointers, so will the arrow come through on video, the mouse?
Yeah.
All right. So I print something, I run infinite loop, and then I print something else after the infinite loop. So you count to infinity, and when you're done, you stop. Now, okay, if you don't believe me, so here is that code. That's exactly what I had. Okay, I'll scroll it up. That's exactly what I had on the slide. Compiles with no problems. Well, it printed before, it printed after, and obviously nobody was counting to infinity. That's too fast to count to infinity.
It was initialized to 0, probably.
No.
Oh, it is initialized to
It is initialized to 1, you can see it up there. Here is Clang. Okay, and Clang 13 actually does it. Okay. Oh, here is Clang 11, and now it's hanging. Okay, so here is your example, by the way, where version of the compiler, they changed how they handle undefined behavior. So as you have just seen, Clang, there is a difference between Clang 11 and Clang 13. GCC always did, well, always, like since GCC 6 at least, it did that. Clang 13 now behaves like GCC. Clang 11 would hang here. Okay, so the slide is a little bit out of date. Clang 13 does what GCC does. Clang 11 does what I say on the slides. Now, which one is correct? Both. The standard doesn't say what should happen. Well, okay, so first I must qualify. According to the standard, with some qualifications I'm not going to go into, infinite loop is undefined behavior. Now, why? So at this point, okay, why would they do that? Well, okay, there are some obvious reasons. There's hardware support, different types of hardware. Okay, fine. Let's give accommodations for that. But why this? Like, why this example is undefined behavior? This will behave the same on all types of hardware. There isn't any hardware that wouldn't support, compiling this code, like one way or the other. Okay, and now we get to the performance part. Actually, the reason that particular example does what it does has to do with performance. So here is some other code. I have two loops here, and as you can see, the body of the loop is exactly, the loop itself is exactly the same. The body of the loop is different. Obviously, I'm oversimplifying. The compiler might even figure out how to optimize this completely, but let's assume that the loops have to run, so bear with me. Now, as written, the overhead of the loop, which is increment of j and comparison of j with n, is incurred twice. it would be a very common and very desirable optimization to combine the loops together. Compilers do that all the time. That's like bread and butter of compiler loop optimizations. There is one slight problem here. And the slight problem is that at compile time, we can't know if the first loop will terminate. Because it goes in steps of 2. If n is odd, it'll never terminate. But if the first loop doesn't terminate, then n2 should not be changed at all. So is this optimization valid or not? Well, it's invalid. Technically, it's invalid. But we really, really want it to happen. So the standard breaks this knot by saying a loop that doesn't terminate, whether it's predictable at compile time like in the first example or not predictable like in this example, is undefined behavior. Now, follow this logic. The standard says if the loop terminates, then the optimization is valid because after we exit, nobody's printing, like there's nothing visible happening in this code. After we complete with this entire chunk of code, both n1 and n2 are incremented to their final values. And if I do the optimization, combine the loops together, the result is the same. So then the optimization is valid. If the first loop does not terminate, there are no requirements on what the outcome is. If I produce the same outcome as in the first case, it's still as valid as any other outcome. So therefore, this optimization has now been declared valid by decree under all conditions, instead of just the conditions when the first loop terminates. Okay, is that part clear? Okay, so that's the logic behind using undefined behavior for this type of optimization.
Small question.
Yeah.
Isn't technically it only does undefined behavior if it's an infinite loop with no side effects or no observable side effects?
Okay, observable behavior has to be preserved. So it depends on, so if it's truly observable, so if it's printing.
So if this loop printed N2 or N1 every time? Well,
yes, then, okay, so observable behavior has to be preserved. Also, it can throw, which is actually one of the exceptions for infinite loops, if you can throw from inside of the loop. And basically, it could throw from the printing. But yeah, observable behavior like printing would have to be preserved. But side effects that are not observable in the middle of this, side effects that are not observable until the end, don't count. So there may be side effects that you don't see during the loop. Those don't count. Okay, so I would love to say, like, never write your code with UB. And unfortunately, in good honesty, I cannot. There are lots of reasons for UB in standard. Some of these are performance reasons. They allow some optimizations. I think there are chairs in the back there. There is stuff that has been declared UB that is only there because of some obsolete hardware that you will only find in the museum today. And it's still in the standard. Okay, who have seen a one complement machine? Like not in a museum. And those who haven't, you'll probably never see one again. And yet it's still enshrined in the standard.
Yeah, you got that in C++20. Signed integer is not defined to be 2's complement.
So is integer overflow still defined? Well, is integer overflow now?
No, integer overflow is still UB.
Unsigned. Signed is 2's complement.
Signed is 2's, okay.
Yeah.
So is left shift now fully defined?
No. Because if you shift bigger than the thing that's wider than the thing you're shifting, then it's still UB.
Okay, so that one is still UB, even though all processors today have a shift left arithmetic, shift right arithmetic, and all of those do the same thing. And there is no way for for you to force C++ compiler to emit that instruction.
Have to think about that.
Do they all do the same thing if you shift greater than the width of the register?
Yeah. Well, all the 2's complements do. Well, I don't know about microcontrollers, but like the mainstream ones do.
Yeah, well, there's a big difference between all processors and mainstream processors.
Yeah, okay. Now, then there are also things that are, or, you know, because there could be bugs in the standard. So you really can't, you really can't put your foot down and say, no, undefined behavior is permitted in our code. Like, for example, until C++11, you wouldn't be able to, C++17, you wouldn't be able to program with unions if you did that. Okay, some hair splitting on the language. Undefined behavior. Your entire program is ill-formed if you encounter this. So if undefined behavior is encountered at runtime, now this is hard-coded. So this example will always be undefined behavior. There is no runtime precondition. If the program goes through this line, it's UB. The previous example where we saw was integer overflow. It's runtime dependent, depends on the data. But if you go through a line of code that with the inputs executes undefined behavior, the entire program is basically the results are undefined. Unspecified behavior, something which is very different. Unspecified behavior means there is a list of possibilities. They are enumerated. One of those has to be chosen. The standard doesn't say which one, but one of those has to happen, nothing else. If you're thinking that like the first one and the second one, the difference is only in like number of possibilities, well, maybe in some, in the way that Captain America is just a muscled up kid from Brooklyn. Yeah, but in practice, the biggest difference is unspecified behavior never, as one of the options affecting other parts of the program are never on the menu. Whereas with UB, they are. So that's the biggest difference. And then there is implementation defined behavior, where the standard actually doesn't give you the list of options, but it says that implementation must complete the definitions. Every valid implementation must augment the standard and define this behavior. They could do it differently. Yes?
I just want to disagree with that it must be well defined. Standard doesn't actually say that. All it says is it has to be documented.
Well, okay, so like don't do it is also, I mean, this is also part of well defined. It's documented means that it's defined. Like you know what is going to happen.
It could be the same consequences as undefined behavior.
It could be documented to invoke undefined behavior. Yes, yes. Yeah, the implementation doesn't have to say that it will work, but it has to say like what is going to happen, including like it won't work or UB. All right, so now we're going to see some examples of interaction between UB and performance. And I'm going to lay out this logic because I'll be basically repeating these bullet points for every example, because that's kind of the logic it follows. So here is what the compiler does. First of all, assume that undefined behavior doesn't happen. Second, from this assumption, deduce the constraints on the state of the program, on the runtime state, like basically on all the values involved. Third, because we just assumed that UB doesn't happen, assume that the constraints are always satisfied. Third and fourth, now that we have the constraints, do the normal optimization stuff that compilers do with these assumptions. If undefined behavior does not happen, constraints were indeed satisfied, optimizations are always valid, and the program is correct. If undefined behavior does happen, the standard doesn't specify anything for the entire program. Again, this is where the entire program comes in. Therefore, even the results that are produced by the code optimized within these assumptions are also correct or valid. Correct. Okay, valid. Let's say valid. Valid. So basically, whatever the optimized program does, if you feed it the data that it assumes you'll never feed it, is still valid according to the standard. So that's what you're going to get. So far, so good. All right. So the other question that, if you go back to your your organization and you start selling this to your teams, I'm sorry. You're going to get a pushback on, well, it never really happens. Who have seen that? And they prove to you that it doesn't really happen. We run it on this compiler, we run it on this compiler, and it doesn't really happen. Well, okay, let's see what actually can happen. So here is an example. And I'll switch to code in a moment. F of integer I and return I plus 1 greater than I. Is this always true? I mean,
The edge case being what happens when I is int max.
Yeah, okay, so obviously it's always true like until you hit the overflow, until you overflow. If you don't overflow, it's obviously always true. Okay, so what happens if you hit the overflow? And actually, if you don't hit the overflow, and let's assume the compiler somehow knows that you don't hit the overflow from some other place in the code, the compiler will immediately optimize this to return true. Right. And there are actually lots of places where the compiler can deduce. We'll see one of those places later. There are places where compiler can deduce that it won't happen. So, okay, now remember our optimization logic. Let's say if I is equal to int max, this is undefined behavior. So we don't have to do anything special for this case. Any result is valid, including doing whatever the program would do if you actually optimize. Well, let's see if that actually happens. Okay, so I'm actually going to show you, I mean, I'm going to prove to you that it does happen, but I'll prove it in a way other than running it, because it's actually hard to prove that by running undefined behavior. You never know what's going to happen. So here are 3 functions. Okay, and look at the top one for now. The top one is the one that F, that's the one with undefined behavior. Okay, I assume everybody here knows how to read this? Okay, who doesn't know how to? Just for me, so I know how much to explain. Who doesn't know how to read x86 assembly? No problem. No, I'm real. I mean, no problem. I'll just have to explain a little more. What I'm doing here is oh, sorry. Sorry. Probably.
Yeah, try Control Plus.
I can, but I need to shrink the screen first. Because after it goes... Is that more? Okay? Okay. So the first one is our function f. Now, So here is what it does. And in order to prove to you that the compiler did the optimization, I actually did the optimization by hand. So see, this is a function g, which is just hard-coded to return true. And we're going to compare the machine code of the two. And if the machine code is the same, obviously they are exactly the same. And it's better than benchmarking or looking at the results because, well, yeah, define behavior in the code. On the other hand, if the machine code is the same, it will do the same thing on the hardware. So looking at the top two, whether or not you can read it, you can see that they're exactly the same. If you can read it, it just loads one into the register and returns, which is true. So this is the immediate operand return called. This is 1. This is the true. This is the value of true. So load true into the register and return out of the function. That's all it does. All right, and so I have just proven to you that the compiler did do the optimization, that I plus 1 is always greater than I. It did so unconditionally, even though if you turned off that optimization and you ran that code with int max, it probably would have overflowed, went back to 0, and probably wouldn't, and then it. So if you actually force the compiler somehow or write it by hand, like integer add instruction, on this hardware, integer add will overflow. But the compiler did the optimization, and I have just proven to you that indeed the compiler did do the optimization. So what's the last one? Okay, we know that the compiler did do the optimization, but I haven't proven to you why it did that optimization. So I said that it's because of undefined behavior. To prove to you that it's because of undefined behavior, I'm going to change the parameter from signed int to unsigned int. Overflowing unsigned int is perfectly fine. It's defined, and it goes back to 0. That's in the standard. That's what it has to do. So now the compiler cannot make that assumption, that I plus 1 is always greater than I. And let's see what the compiler did. Okay, the compiler, this is not straightforward. There is some optimization going on here, but CMP is a compare. So the straight up implementation of that function would use another instruction that we'll see in a couple of slides, but you can see the compare is there. So okay, so I have just proven to you that the compiler indeed optimize this code to always return true, even in the case of int max. And I have shown to you that compiler relied on undefined behavior to do so, because if I remove undefined behavior, the compiler has to basically has to honor this overflow possibility. Okay, here is another one, and you will recognize this if you attended Chandler's talk. I mean, he stole it from some BSD. I stole it from him. I've simplified his example a little. So here is a substring comparison function. And again, this will be again related to performance. Now, it's obvious why the previous one was related to performance. That CMP is not free. Returning hard code return 1 is cheaper. So that was a performance optimization by the compiler. This one will be even more so. Okay, 2 string pointers and the maximum length of the string. This is a substring comparison function, which means they're pointing to the same string, just different places. Okay, going to run the loop, and if the characters are different, I'll return the result of the comparison. if the loop ends, then I'll return false. Null terminated, so null terminated string. All right. There is an inefficiency here. And the inefficiency is because they're pointing into the null terminated string and to the same string, one of them, the 2 pointers as they're advancing, is going to hit the null before the other one does, because there's only one null. And null is less than anything else. So even if the 2 substrings were the same up to that point, one of them is going to hit null, at which point the comparison will terminate. So I don't need the bound check on the index. If I let it go unbound, in reality, it's not unbound. And that's precisely because it's substrings in the same string. If it wasn't, I would have to give it well, if it wasn't, it would hit 0 on the other one. But if they were not null terminated, then I would have to give it a bound. Okay, so this is just pure unnecessary work, that comparison. But the compiler cannot remove it because it doesn't know that they point to the same string. As a programmers, we do. So we're going to remove it from the code. Okay, now it's not going to fit on the screen. All right, so Google benchmark. Who here doesn't know how Google benchmark works? Okay, a brief explanation then. All right, so this is benchmark fixture. There is nothing special. They're just freestanding functions. The interesting part is here. This loop runs basically until the benchmark accumulates enough measurement data and decides to stop. This is what we're measuring. Don't optimize doesn't mean that the code inside not optimize. It means don't discard results. Because one of the things you'll find if you use this benchmark, compilers are really good at figuring out that you're computing the same thing over and over again and assigning the same number to the same place over and over again. And they'll say, okay, let me optimize this for you. I'll leave only the last one. And this is just us preparing some string. Okay, and we have this function, well, compare int. In our case, compare int. That's the one we want. That's the optimized one. That's what I shown you as the optimized one. 2 pointers, no length check. Oh, sorry. Same 2 pointers with length check. Four. Okay, yeah, I should have commented out. Okay, ignore the middle line for a moment. Okay, this compiler doesn't do that. This compiler doesn't do that optimization. Huh. That's what happens when you upgrade the compiler a few days before. Okay, they turned off this optimization in this compiler. This time, all right, I'll have to switch the compilers. This is Clang 13. Man, I did everything on Clang 11, and then I upgraded to Clang 13 for my coroutine stock, because Clang 13 has a little fuller support for coroutines, and they changed all the optimizations on me. All right, so this is what I got from Clang 11. Original with the length check was doing 2 billion comparisons per second. Optimized without the length check was doing 1 billion comparisons per second. That's one hell of optimization. Okay, if we have time, I'll go back, change the compiler, and rerun it and show it. Now, incidentally, someone else was working on optimizing the same code, and for random reasons, they used int as an index instead of unsigned int. Or actually, wait a minute, I think it might have worked because... No, it didn't. Okay, so yeah, so I have to look at the compiler. Okay, so int as an index. So the previous one was unsigned int. Why unsigned int? Well, indices are never negative. Why give up half of the index space for nothing? Why int? That's because what you normally write automatically when you write for loops. And again, no range check. And this version runs at 3 billion comparisons per second. So this one actually is optimized. Okay, it would be interesting to look at the assembly for what Clang 13 does. This is what Clang 11 did. So what Clang 11 did, on the left is unsigned int. This one here was the arrow. On the right is int. The one on the left, specifically the instruction marked by the arrow, is a 32-bit unsigned integer addition on a 64-bit platform. The one on the right is actually 64-bit unsigned integer addition on a 64-bit platform. The 32-bit unsigned integer addition is slow. That instruction, LEA, stands for actually load and extend address. It wasn't meant for additions. It was meant for address arithmetic, for computing basically offsetted indices, like offsetted pointers into arrays. So its original intent was to, given an index, given the beginning of the array, the pointer, and the index to the array, to compute the address of the element. It's it's basically like cruelty to use it for integer additions, but that's the only thing you have on x86 if you want to have 32-bit unsigned integer add. 32-bit is important here because 32-bit unsigned int is well defined, and if it overflows, it has to go back to 0. An overflow happens on the 32-bit boundary. 64-bit unsigned int, of course, is also well defined. If it overflows, it goes back to 0, but it happens on 64-bit boundary, and that's what the hardware normally does anyway. Signed int, the standard just says it's undefined what happens. So here is what the compiler does. The compiler says, okay, if you used unsigned int, then I have to give you your overflow, correct overflow, and therefore I have to use that LEA. It's about 3 nanoseconds to do that instruction versus 1 nanosecond for the normal add, and in reality half a nanosecond for a normal add because it can do 2 at a time. Okay, so in my opinion, yes. See, it comes down to if you write a loop and the size isn't a big deal. Basically, if you run a loop and you know that it's not going to be billions one way or the other, what should you use? I always use size t, but I know a lot of people who just automatically write int. In reality, both work fine. Size t works fine in this case. Int works fine. What you shouldn't do is use unsigned int that is narrower than the native hardware width.
This is completely machine dependent, or is it going to be?
Well, it is machine dependent, and as we have just witnessed accidentally, to my embarrassment, it is also compiler dependent because some compilers apparently don't do this. So now the question is, why removing that index comparison, I less than L, actually degraded the performance? Because the compiler figured out that the integer overflow, unsigned int overflow, will not happen if you have a bound in the loop, because whatever L is, it's no greater than unsigned int max. Therefore, we'll hit that boundary before you hit unsigned int max. Therefore, you will never overflow. Therefore, the compiler went ahead and did that same optimization. It replaced rounding, so overflowing add, with a straight up non-overflowing add, knowing that the overflow part will actually never come into play. And so this is a performance-based optimization that the compilers do if you let them. There are actually several ways to let them, only one way to not let them. But see, the compiler exploits undefined behavior here. The compiler with a signed int, without bound check. With a 64-bit int, of course, the compiler just uses native 64-bit add, and then what happens on 64-bit boundary, the hardware does its normal thing. With a 32-bit int, if it's signed, the compiler says, if you happen to overflow, all bets are off. In this case, I'll just let the hardware do the cheapest thing. What this will do is it will extend into 33rd bit. The instruction is 64-bit add, so it will just extend into 33rd bit and keep going. Of course, when you assign it to 32-bit back, it will truncate, but the add itself will just extend into 33rd bit. If you write unsigned int, that's well defined. The compiler is forbidden from doing that optimization. It has to do it the hard way. So again, compiler does, this is a more non-trivial optimization. The logic here is kind of longer, more convoluted, but the same logic.
Would there be any value in using signed size t instead of unsigned size t?
Is there any value in using S size, signed size t, S size t versus unsigned size t? Not in this case.
But just in the general case, like if you're really trying to optimize for like a set of sensible defaults.
I don't know. I mean, well, so size t is defined as the maximum size that can be used for index. It's not necessarily the maximum size that the hardware supports. So, the game here being played is like the overflow will basically do the right thing at the hardware limit. Anything before that, you have to do special tricks. So basically the question in this context, so in general, there may be lots of other considerations. In this specific context, the question boils down to, can it ever be that size t isn't the maximum word size? In theory, yes. The standard doesn't require that it is. I've never seen it, but in theory, it's possible. Okay. All right. Yeah. So another, enough of integer overflows. Let's look at something else that is reasoning from UB. Because we're going to get to basically what Marshall was itching to from the first slide, how the undefined behavior taints the whole program. Because so far we basically screwed up the point of execution. All we have seen so far was we were able to damage the point where undefined behavior occurs, and something, well, okay, we should have expected anything, but with our reasonable, in quotes, expectations, something happened which we didn't expect. Now we're going to break even that. All right, so here is my function takes a pointer, increment what's pointed to, and then returns either the value or null, depending on whether the pointer is null. Okay, you've seen, you probably don't write that exact code, but if it's scattered across maybe two functions, sure. Yeah, quick.
I had an example that matched this reasonably well, except that the person who had written it was very careful not to increment that, except in the case where the pointer was not null. And then somebody came along and logged the value that p was pointing to at the beginning of the function.
That could happen. Actually, the other thing is you actually do write this code. You write this code often, and you write this code if you call delete p, because delete has a built-in null check.
I have a great example for you. I'll show it to you after the.
Yeah. So so you actually do write this code. You just don't know it. If instead of return p, if you put delete p underneath, you've written pretty much that, only with a different outcome. But delete has a null check. All right. Oh, sorry. So here is that code. That's exactly what I've shown you on the slides. Okay, let's go. This time I'm going to compile it with GCC. Okay, whether you know x86 assembly or not, the mnemonic for comparison is CMP. So notice what's not there. The important part here is not what's there, but what's not there. There is no comparison of the pointer. There is, okay, move something into the register, add is that plus here is our 1 hard-coded into the instruction, that's the return. What's not there is the CMP, or actually the other option would be the test and jump on bit. So for those who know x86 assembly very well, doesn't have to be CMP. Yes, I know you could write on a status bit from a previous instruction. That's not there also. Again, I could prove it to you by removing the question colon operator and compiling it. And it would generate exact same assembly. So on the left is the one with the question colon, and on the right is the one without question colon. Generate exact same assembly, which means that the compiler removed the question colon operator. Why did the compiler remove the question colon operator? Well, because we just told it that p is not null. How did we tell it that p is not null? Because star p would be undefined if it was, and if it so happens, then all bets are off. Returning star p is as valid as anything because it's undefined behavior. And if p is not null, then question colon is unnecessary. So the compiler did that optimization. By the way, this comes down to one of the biggest arguments in C++ programming. Do you do null check before calling delete on a pointer? Anybody had that argument in your organization? For performance, do you write if p delete p? Anybody ever had that discussion?
Yeah.
The answer is it doesn't matter, because the compiler will do that for you. It will remove the second check anyway, just like it did here.
And it probably inlines it.
Well, of course, that's the reason why it removes the second check. But yeah, it inlines it. But if you write if p delete p, the compiler will just remove the check from delete. Well, they're both the same, so whichever one, remove one of the two. All right, now we're getting to the moment you have all been waiting for. So far, taint from UB propagated forward in time. Now I'm going to make it go back in time. I flipped the conditional check in this program. So I said, if p is not null, then increment star p, which is a reasonable thing to do. I'm protecting myself. And then I said return star p, which again you would never do it like that, but maybe this is hidden. Maybe you're calling some other function to do this, and inside that function they protect against null pointers, so things like that. Okay, so now this is the code. I'm guarding the first line, and then I'm returning star p unconditionally. Again, the interesting part is what's not there. That check for if null is gone. Well, if you want me to prove that it's gone, I'll remove it myself. I'll compile it. Side by side. So, okay, as you can see, they're exactly the same. So I have removed myself the check for P, compiled it, and it generated exact same assembly. You know, all of this again is these are all optimizations. This is all done for performance. So the compiler removed this check, the check. What does it mean in practice? In practice, it means you're running this thing under debugger, and it's going to crash, but not where you expect it. It's going to crash earlier, which means I just made undefined behavior taint a perfectly valid, see this line, if p plus plus star p, this is perfectly valid code. There is no undefined behavior here, and it's going to crash on that line. So I just made undefined behavior, which actually hasn't happened yet, because we haven't executed that code yet. We will execute this code, but we haven't executed it yet. I just made that future undefined behavior travel back in time and taint previous line in the program, which was perfectly valid. So this is the example of invoking, and not just invoking. Like, I haven't actually invoked it yet, but I was inevitably going to invoke it. The inevitably part is important. If there was any way for me to deviate, then the compiler could not do this optimization.
If this was a pointer to some big-int class which might throw on increment, then you wouldn't have that happen.
Right. Yes. If there is something between these two lines, if the compiler absolutely cannot be certain 100% that that something in between does not throw, then it can't do this optimization.
What if there's a side effect, for example, an assignment or something?
Again, what happens if there is a side effect? Side effects are not immune from the wrath of UB. Side effect also, whether it's done or not or how it's done becomes undefined itself. So, you know, yes, if there was so one thing is like, let's say increment operator printed.
Yeah, suppose you assign to an unrelated variable, so I is 0 or something like this.
Well, that by itself does, you know, that's not observable, right? But like, for example, if increment printed, then it could throw, and then it would, it has an alternative way of bailing out from that piece of code without encountering undefined behavior. So, you know, undefined behavior travels back in time kind of only on a linear path. If there is a fork you're going from the present to the future, and undefined behavior is only on this path of your future, then you can't cross that fork. The entire branch is tainted, but because you could have taken the other multiverse, the other universe in the multiverse, and you could have lived here, then the common part of the two branches cannot be tainted by UB. The compiler can, in theory, propagate it up to the fork and do some nasty stuff about that, but it can definitely, like, for example, if you can exit by throwing, that is a hard boundary.
Is it important to note that this is still not guaranteed to happen? It's not guaranteed to optimize in this way.
Oh no, it's not guaranteed to optimize. What's important to know is, see, I'm trying to narrow down this gap between UB can do anything and it's terrible and you should just avoid it like a plague, and UB is just code. I'll get UB is just code, and whatever it does at the end is what it does. I'm trying to kind of basically give you arguments to defend against both, in a sense. So I'm showing you how the performance optimization does taint the entire program. It doesn't have to, and it could do other things. It doesn't have to manifest this way. But here it manifested itself in particular that a perfectly valid line of code, actually, if we actually were to run this under debugger, it would crash on the first line of the function, and it really would. Well, you've seen it. Conditional check was removed, so it would dereference a null pointer. So it doesn't have to, but this is one of the things that might happen. Yes?
Yeah, I just wanted to highlight, having spent weeks going back, trying to work out why a particular code review failed to catch basically this scenario. The big risk here in code maintenance, as I see it, is that you can have tens of thousands of lines of code, and the more code you have, the worse it is, diligently checking each dereference of a pointer. All it takes is one engineer forgetting to do it once in a visible line of code.
And the compiler reasons all the way back as through the linear segment of the program, yes. Yep. I mean, for obvious reasons, I'm writing it very short, but I could put a few hundred lines of code in between, and as long as there is no way to exit from there, it would do exact same thing. Okay, now so now we're kind of coming to the flip side of it. We understand how UB taints the entire program. We've seen an example of UB tainting the program backward in time. Let's say I want to exploit it. I want to actually help the compiler do these optimizations, and I want to say, okay, these conditions are definitely undefined, so I want the compiler to optimize. If you want to play that game, well, you are playing that game whether you want it or not. Looking at this previous example where I told you, if you write delete after an unchecked reference to a pointer, you are playing that game. But if you want to, steer the compiler in the right direction, it's important to understand what the optimizing compiler can and cannot do, which restrictions it labors under. The biggest one is the compiler must ensure that optimization does not change observable behavior of any valid program. Two parts are important, observable and valid. We already dealt with valid, which means if it's UB, change away. But if it's not, the observable behavior must not change. Okay, observable behavior, the standard has a list, but basically your prints, volatile references for those who are into it. Few more things, not important right now. But the important part is the compiler must be able to prove that optimization is valid under all possible set of inputs. Not that you know that it's valid, that the compiler can prove that it's valid. There is a big difference. David Abrahams touched on that, and he mentioned about references to objects that could be changed while you're looking at them. So we're actually going to see that example. So here is a very similar example on the code. Very similar in that if a pointer is not null, we call something and then we unconditionally dereference the pointer. Not going to be optimized. Why not? Because it's possible that the pointer p, even though it's our parameter, is aliased to something else that is accessible through the function g. I mean, p could be global for all you know. And therefore, yes?
If whole program optimization is being used, could it optimize that?
In theory, yes. If it could prove that g does not change the value of p, it could do the same optimization. The difference between this example and the previous one was that everything was inlined, and it saw that nobody changes the value of p. Here, generally it doesn't, but yes, if it could analyze the entire, so it needs to know what g does, and it needs to know where p comes from. It could do that. there are some restrictions in the standard on aliasing that, and type binding that come into play here, but assuming they all play out in your favor, it could optimize it. But the other thing is, G also might throw, in which case you would actually never return star P, in which case the fact that it's null never comes into play. It could be null without invoking undefined behavior. Again, if the compiler saw the entire body of G and everything it calls and knew that it doesn't throw, so this optimization is theoretically possible. Yeah?
So if I have the example written like this, can G really change the value of P? Because like if P is a parameter to the function.
But P is a global pointer.
Theoretically.
Doesn't matter.
See, P is also a global, P is a global variable.
But not in this case, right?
No, at the call side, the caller invoked f with a global variable. Somewhere I have int star p at the top of my file.
Yeah.
Then the caller said f of that p,
Yeah.
and the function g is in the same file, so it sees that value of p by virtue of file static.
But the check that you do here
It's working on the copy of the pointer.
is exactly is on the, so if it's written like this, the P cannot change because it's local.
Oh, you mean that that copy of the pointer cannot change?
Yeah.
Yeah, that's actually true. Yeah,
So
sure. Yeah.
if
Okay. Yeah,
if
you're
it's
right.
a
Yeah.
parameter, then it doesn't work. But if it's not a parameter, if it's really a global P, then
Yeah. Okay. Okay. You're right. Yeah. In this case, yes. But G could still throw. Okay. So you're correct. Yes.
Exactly. Right.
Yeah.
G
Okay.
can still throw, yeah.
Okay. There was another question back there.
I was gonna say, yeah, the reason this doesn't get optimized is because G might exit, or even
Well,
if
sir-
you turn off exceptions, G might still exit.
Gmas might, well, if it exits, it's okay. Yeah, and P is null. Well, no, that would actually be a valid optimization because, well, okay, I don't know. Is exit considered observable?
Yeah.
Yeah, oh yeah.
Like, no, but like calling return from main is of course observable. But is exit?
Yes.
Okay, then it can't.
It's an IO function.
Yeah.
So
Really?
suppose we were passing it by int star reference,
Mhm.
and
Yeah.
so the possibility for G to modify comes back. Does that become an argument against global variables?
Argument number 1,199.
Well, many others, but another one
Yes.
is it could potentially.
Okay.
become-
Global variables in general impede a lot of optimizations.
Okay.
Yeah.
This is just one example.
Yeah, global variables impede a lot of optimizations.
And aliases to global variables, like references. So
Okay.
it's like, oh.
Did not mean to imply that they were a good
No.
idea to begin with, but
Okay, here is another one. This one is a little tricky. Taking an integer, so I have a function that takes an integer by const reference. Inside my code, inside my G, I make a copy of that integer. I call the function f on the original, takes it by const reference, and then I compare the copy with the original. This will not be optimized. Even though I clearly said that f takes the argument by const ref. I'm very clear that I'm not going to mutate x. And yet, compiler will not optimize it. Anybody knows why?
Const cast.
Because you can cast the const away without invoking undefined behavior unless the object was defined as const at the point of its original definition. Casting const away from something that is const is undefined behavior. So this is well defined. Now, if I did this and then I called f on y, in theory, it could be optimized. I haven't seen a compiler that takes advantage of it. But if I said const int y equal x and then I called f of y, doing a const cast there is undefined behavior. The compiler can assume indeed that the const cast does not happen and can optimize it to return true. Okay, I haven't tried Clang 13 obviously, but Clang 11 and GCC 11 do not do that optimization. Okay, so in the last 15 minutes, let's talk about now that we kind of understood basically where UB comes from and how it's related to performance, let's talk about, if it's related to performance, is it something that you can use yourself for the same purpose, for the purpose of improving performance? So basically, can you, not invoke UB, but like embrace UB, if you will, with the purpose of improving performance? I'm not talking about actually intentionally causing UB in your C++ code. So I'm talking about embedding undefined behavior in your design to improve performance. Yes, and in order to understand why, you have to understand broader sort of what undefined behavior is. In C++, we know what it is and the standard says, but in general, your program is designed and specified to produce certain results which depend on input. Your specification for every valid input describes what the results are. And that is your contract with the user. You obviously do it without listing like every valid input, you do it in general terms, but that's the effect. For every valid input, you define what the results will be. In what I just said, there is one thing missing. So in every valid input, you must define, for every valid input, you must define the result. What's missing?
It's not all inputs.
Yes, specifically what's missing is the definition of valid. It's not enough, and this is actually people miss in functional specifications all the time. It's not enough to specify what is the output for every valid input. You have to specify what constitutes a valid input. It's part of the same contract. And now you can view undefined behavior as simply going out of the spec of the contract, giving the input that is outside of the terms of what's defined as valid. That is basically the undefined behavior. If you have a contract that includes the domain, in the mathematical sense, the domain, the range of valid inputs, and you get input that is outside of the domain, that is now undefined behavior because the contract specifically said, under these conditions, this is what will happen. And not under these conditions, I don't know. I didn't say what will happen. Well, okay, in your own program, in your own specification, what do you want to happen? You basically fundamentally have two options. One, you can, well, assuming you're not redefining it as valid. So I'm assuming you're settled on what's valid. You could say, I'll identify that it's invalid and handle it, reject it with diagnostic or correct it, handle it somehow. That's part of your contract. It's not undefined behavior. You have the other option is, I will not detect that it's invalid. I will proceed to operate on the assumption that it's valid. And this is actually what we've seen over and over again in our C++ examples. With that pointer dereference, with the integer overflow, the compiler would say, I'm assuming that you're giving me valid values. I'm generating code proceeding on these assumptions. If you give me invalid values, it's still the same code. Whatever it does, that's what you're going to get. So you can do the same thing. Why would you do it? Well, the reason you would do it is exactly the same why like half of C++ undefined behavior does it. Well, okay, I don't know about half. Yeah. But the reason is the same, performance. Validating preconditions may be harder than solving the problem assuming the preconditions are true. One example that we have actually seen with like our first example of undefined behavior, the infinite loop, well, second example, is if your precondition is the program must terminate, it's impossible to prove, but it's easy to actually test it for, like in practice for this particular program and this particular input, but it's impossible to prove it in general. So now you have a precondition that you cannot validate. So if you have some tool for which the input is program, and you say precondition is that the program is terminates, what do you do if the precondition is violated? You basically have to embrace undefined behavior at this point. Okay, I'll give you an example. Actually, this actually comes from my work. So I want to convert this picture into a graph. The squares are nodes, the lines are edges. And when I say picture, I mean like the drawing, like that. I have all the optics stuff. So I'll convert it into a set of rectangles and lines. So all of that I got. Now I'm just converting it into a graph. Pretty easy to do, for all the rectangles and for all the lines, check the endpoint coordinates of the lines, compare them with the rectangles. There are computational geometry algorithms for doing it at scale. Let's assume that I am representing my graph as like a vector of pairs, so basically edge table. Each node, as you can see, has a number, so each edge is just a pair of numbers that it connects. Okay. That's the question there? Okay, that's easy. Now, what are my preconditions? Well, here is one. Because I said that graph is a pair of numbers, vector of pair of numbers, I implied that this doesn't happen because there isn't a second number for it. I also implied that this doesn't happen because I didn't specify how to handle, if it did happen, what do I do? Do I go by endpoints? Do I go by any interaction between the box and the line? Does this edge connect three nodes of the graph? So none of these were specified. And of course, you could have a line that doesn't touch any boxes. So now I have two options. I could specify what it does, including defining that this is invalid input. I could actually say this is invalid input, and I'll tell you exactly where in that picture invalid input occurs. The problem with that is doing that validation takes about the same time as actual conversion of valid input to the graph. In this case, it's not like exponentially harder or even n square harder, but it's exactly equal. And my users who give me valid graphs don't want to pay for it. So my users say, well, sure, the validation is nice for somebody who makes this sort of mistakes. We have the correct by construction procedure, which guarantees that these mistakes don't happen, or if they happen, they get caught earlier. And they may be entirely right about it. They may have a validation tool. They may have a generator that generates these that doesn't make that sort of mistakes. So they say, you doubled the runtime because you were concerned about that guy, but there is no benefit to me. Take it out. So now, what do I have to do in this situation? Well, what do I do is, first of all, I'm very clear about my contract with the user. I say, these are invalid inputs. Whether you think you do this or not, if you do, okay, what happens if you do? Because I don't want to pay that penalty for validation, I'm saying if you do, the results are undefined. I don't say unspecified because I really don't want to be bound by what my current implementation would do with that sort of input. I say results are undefined. And now I have a big uphill battle in front of me because they figure out what the current implementation does, and then they try to keep me to that. But I say the results are undefined. And then I have a choice. Do I detect violations or do I not detect violations? Well, obviously, if the detection is cheap, I do it. In my case, detection is not cheap. The best solution is to provide optional validation tools, which the users can deploy on their dime and by their decision. So, okay, if you want to validate, yeah, it'll cost you double the runtime, but you can do it. If you don't want, it's on you, and if you hit undefined behavior, don't come back complaining. All right, so now we came up with this optimal solution. Define valid inputs, declare that the rest is undefined behavior, provide optional validation. How about applying that idea to C++, going back to C++? Well, it turns out that that has already been done. Yeah, UBSan. So here is our favorite integer overflow with k plus 10. By the way, anybody knows what that is for? Any guesses?
That's to defeat the optimizer.
Exactly. I haven't seen any compiler so far that know that rand returns values between 0 and something.
Is it cheating that I just read your book?
So this is currently my favorite way to define the optimizer. I'm sure somebody here thinking, oh, I must put that optimization in my compiler.
Yeah.
Don't you have to fire the seed off, otherwise you get the same answer every time, and the optimizer may see that?
Well, first of all, you will not get the same answer. It'll keep rolling forward.
Well, yeah, same order, yeah. But each run will start off with the same value.
There is only one here.
Right. So it'll be the same value.
No, but see, I'm talking about compiler optimization. Compiler doesn't know whether it's source of where it's source of randomness. Just like compiler doesn't know that it returns positive numbers, it also doesn't know that it's actually like where its default seed is coming from.
Today.
Rand is just a function as far as it's
What?
concerned.
Well, the compiler has kernel knowledge of the C library, but it may not know about this.
Okay, fair enough.
Well, it knows a few things. It doesn't like.
Right.
Yeah, it doesn't.
It
It
doesn't necessarily know that.
yeah.
It knows lots of things.
It knows lots of things, and sometimes it starts making assumptions like you don't pass null pointers to memcopy, and then all hell breaks loose.
That's one of my favorite examples.
Okay. All right, so that's actually okay. So Clang 13, worked in this case. So here is what I did. Okay, so all the normal arguments, I said fsanitize equals undefined. Here it is. That turns on the UBSan. I ran the program. Now, as we know, this is not necessarily undefined behavior. It's only undefined if k is large enough. So no static diagnostic can be issued. No static diagnostic should be. Anybody who tries to issue static diagnostic to you on this is wrong. Runtime error. Pretty decent.
Right.
Integer overflow, it even told you what the value of k was. So undefined behavior.
And it'll give you a stack trace if you had a stack.
It will give you a stack trace. There is a specific like internal function they call you can stop on the debugger.
Right.
Like you can put a breakpoint on something, and if you're in the debugger, it'll stop there. Okay, so the bottom line. Basically don't mystify don't like apply any supernatural qualities to UB, but take it seriously. It's only a program executing out of contract, nothing more, but also nothing less. Never assume that just because it works, it's not really UB. And when you are on the other side of the table, when you are the one writing the contract, remember to specify not only the defined behavior of the program, but what would make it go into undefined behavior, what constitutes invalid inputs, and if you cannot validate the invalid inputs cheaply, provide sanitizers, optional tools for validating your inputs that the user could run. And again, going back to the other side of the table, if you are the user of that, take advantage of the optional input validation tools that somebody else provided for you. Okay, well, so the book was already mentioned. There is a chapter on undefined behavior in this book here. And with that, thank you for coming, and questions, and I'll be available through the entire week. Yeah, Mark.
I just wanted to touch on something that you said because it's something that I've seen people get bit on a lot. You know, your section on you know the compiler is able to tell this pointer is not null because you indirected through it. There are other ways that the compiler can tell that a pointer is not null that people don't think about. The example you gave was pass it to memcopy. Memcopy has a contract that says neither the source nor the destination pointer can be null. That's the C standard defines that. The compiler knows that. So if you pass a pointer to memcopy, the compiler will say, I don't need to check it for null because I know it's not null because you passed it to memcopy.
Imagine a similar case is for references. If you dereference a pointer into something that takes a reference.
Well, applying star in any context.
Yeah, applying star.
Applying star in any context
But
is
if you call memcopy, even with a length of 0.
technically yes. Although the one time the compiler vendors tried to do that, they got beaten over the head so heavily that they.
No.
Linux kernel does it.
Yeah, well, both Clang and GCC will optimize that.
No.
Yes.
They put it back in?
Yes.
Because they did it in GCC 4. Something and then they had to take it out.
Right, and now it's back.
It's back?
Yes. Even if the length is 0. Yeah, just the optimizer knows the standard better than you do, better than I do, better than everybody does.
Okay, any other questions? Yeah.
I always tell to students that undefined behavior is caused by our weakness to define the proper type systems. I mean, if we would have a type pointer, not zero, not null pointer, then you could just make it part of the type function.
In some cases, but in the example that I've gave you with whether the program terminates or not, no type system or nothing else in static analysis would help you there because the problem is unsolvable.
It's just a very complicated condition.
Yeah, so you cannot prove in polynomial time that the program terminates.
You can't prove it at all.
Well, it's exponential. But you would be asserting that your program terminates, which is actually exactly what you do. Now you assert the same thing by just writing it. There is implicit assertion that the program terminates. The standard holds you to it.
Unless you apply never to a function. Like I said, terminate at some point.
Anything else? Oh yeah, there's a question in the back.
I'm just trying to get a handle. I can't quite see it. Is undefined behavior harmless in some scenarios? Or because you kind of sort of said on one side, you can have odd things happen. On the other side, you can kind of use that. But is there cases where you can say in a large production system, if I run UBSan, it shows undefined behavior here, there, and everywhere, but the system doesn't seem to
No.
suffer from it.
Okay, so is undefined. No, so when I'll get to you. So when I said you can use it, what I mean by that is, like I've shown you in my last example of like me using it intentionally. You can use it in the sense that it's a way to signal to somebody in C++, to the compiler, if you're writing the contract to your users, that this will never happen. But then you actually have to hold true. If it does happen, you're out of contract. So yeah, if you actually have UBSan errors in your program, you should definitely fix them. But
well, I'll give you an example of one error that's in there. They're rotating through a set of enums, right? The old style enums. And to say less than as the terminating conditions, you're actually going into an enum that doesn't exist, which is UBSan behavior. But it doesn't, it's easily fixed.
Yeah.
I fixed it, but it didn't seem to have any, the whole program didn't just...
Again, the compiler is allowed to assume that that condition is always false and reason backward from there.
How would it reason backwards? In a bad way. So in other words, they do actually reason through that. It's a set of nodes, right?
They would remove the comparison.
That doesn't happen.
In this case, in this one, In this one, it doesn't, but they're allowed to remove the comparison. And then if you actually do it, it will basically go in.
Undefined behavior made by two, but it's just not yet?
Yes.
Oh,
Yes.
not ever.
Or maybe not ever.
Possibly. And that's the hard part, because you have to have, you have to have discernment about it. Because, for example, so in your example, no, this is an optimization which they could do. But like accessing an array element through a reference to another array element. Well, and I'm using that one because they already mostly fixed it in C++23. That was like entirely undefined behavior. But the problem is that std vector violated it all over the place. So you have to use some discernment in your analysis of what undefined behavior you can ignore. Now, fortunately, UBSan, if anything, errs on the side of underreporting. I have never seen UBSan report a gratuitous error, like one of those things where it really shouldn't have been undefined behavior in the first place. They should fix it in the standard, and sometimes they do. UBSan only reports the true ones, at least that I've seen so far.
I've seen
Okay.
a false positive in submap, I think, once with UBSan.
Oh, UBSan reported? Oh, well, in submap you could get an undefined. I mean, are you sure it was false?
I'll double check.
Okay, in the back first.
So I just lost. I'd like to see it. Peter. Yes, I want to respond to his question in particular. So the way I've always told people about this at my work is that
I see,
if you
Eduardo.
have a concurrency error, it might work for a year. It might work for 10 years. And then one day you put it on a different architecture and it breaks. And UB is the same kind of issue. It's a bug that is latent, but it's not a bug.
The funny thing is I am moving this stuff to a new architecture. That's why I went to UBSan and Diagnostics.
Okay, Eduardo.
Yes, one example of annoying undefined behavior is that sometimes you want to call a function that you know, because of the argument that you're providing, won't throw an exception. Let's say that you're doing an allocation and you are certain that the allocator will have enough memory, okay? And one technique that reduces binary size and so on is to do a cast from the function pointer using reinterpret cast to the version of that function pointer that is no except.
Well, reinterpret casts are basically UB kind of by their implementation defined to begin with. So on your best day, you are an implementation defined world.
This is something that has caused trouble because it is one of those things that we had to make a UBSan not to report.
Well, okay, so reinterpret cast is implementation defined, which means the implementation itself is now fully responsible for both stating the results, giving you guarantees, and holding you to those guarantees. So I would argue that that is a bug in the implementation. So either you're really doing something wrong, or it's a bug in the implementation where they said this is valid on our implementation. They said reinterpret cast does X, and then they're warning you about X anyway. That could be.
C++17, it feels like it's a valid warning because the two objects, even if they were the same address, which they couldn't be, the accept and no accept version are fundamentally different objects, and therefore you're now saying I was pointed at object X, which.
Have you tried to launder it, by the way?
Now it's at 50. Once you launder, you have to launder everything. So.
Well, you can try to launder that, which should basically erase compiler's memory of what it used to be. So you could try to launder it. Launder pairs with reinterpret cast. So you could try to launder it and see if it basically. Your problem is UBSan remembers too much. So you could try to launder it. I don't know if UBSan actually recognizes launder is a compiler intrinsic in reality. So I don't know if UBSan knows what launder is and is mated properly with that compiler intrinsic. You would have to find out.
Okay.
Okay, there was another question. Marshall, was it you?
I had a comment.
Okay.
And yeah, I have a talk about undefined behavior I gave here probably 6 or 7 years ago, But one of the takeaways from that was, to me, the worst, absolute worst kind of undefined behavior is it appears to give correct results. Because then it's like, well, it works. That's great. I'm done. But
Works on my
no,
disk.
no, you upgrade your compiler and it stops working. You change your optimization level, it stops working. You define some macro, it stops working. You go to a new compiler, it stops working.
You get a different computer, it
Stop
suddenly stops working.
working, right. And everybody, you say, oh, grumble, 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 compiler engineers can't get anything right. When really the problem's in your code.
I had a beautiful one of those, which was my revelation that I cannot code at 2 in the morning. And
Yeah.
it was a crash on a production lottery system.
Oops.
We're overtime.
Yeah.
Yeah.
All right, thank you.
Yeah, thank you. And again, if you want to talk to me, just I'll be here all week.